To recall from the previous lecture, in this example, we have completed the design process 1, 2, and 3. In this lecture, the resistance of the given beam is checked towards bending and shear buckling are described. We will refer the details properties of the ECS571 section in here. To ensure the designed beam can resist the designed bending moment. Clause 6.2.5, EC3 Part 1.1, stated that the design value of the bending moment, MED, at each cross-section, shall satisfy as shown in ECS6.12, in which MCRD is the design resistance for bending moment. The selection of the MCRD is depending on the cross-section classification of the designed beam. As you can see, for class 1 and 2, the MCRD value can be calculated according to equation 6.13. Meanwhile, for class 3, the MCRD value can be calculated according to equation 6.14. Finally, for class 4 section, the MCRD can be calculated based on equation 6.15. Since beam section belongs to class 1, plastic moment of resistance, thus, MCRD is equivalent to MPL, RD, as given in equation 6.13, as shown here. Finally, the value of MPL RD equals 246.1 times to the power of 6 nmm. Therefore, it can be concluded that the beam is capable to resist the designed bending moment as MCRD 246.1 kN greater than MED equals 158.4 kN. Next, we need to check the shear resistance of the proposed beam. Due to excessive shear forces, usually adjacent to supports, the beam may fail in shear. In steel beam design, the resistance of shear is carried by the beam web. The web can fail once it reaches the tension and compression yields, together with the formation of plastic hinges, for class 1 and class 2 section. However, if the web is class 3 and 4, which have thin web thickness, the web will fail by buckling in the shear zone. This picture shows the example of vertical web buckling. The design value of the shear force VD at each cross-section should satisfy clause 6.2.6, equation 6.17, EC3 Part 1.1, where VC, RD is the design shear resistance. For plastic design VC, RD is the design plastic shear resistance VPL, RD as given in 2. However, for elastic design VC, RD is the design elastic shear resistance calculated using equation 4 and 5 in EC3 Part 1.1. The design plastic shear resistance, VPL-RD, given by an equation 6.18, where a V is the shear area given in 3. The shear area is calculated depending on the cases given in A, B, C, D, E, F and G. In our case, the beam is categorized under case 3A, that is rolled I and H sections, which is load parallel to web. For class 1 section, design plastic shear resistance, VPL, RD, is given by equation 6.18. A V is the shear area, as the section is a rolled I and H sections, and the applied load is parallel to the web. Thus in our case, a V can be calculated using equation 3A. Finally, we determined that VPL-RD is larger than VD, thus the beam able to resist the design shear under the applied loads. Clause 6.2.8, EC3 Part 1.1, provide the guideline on the resistance of cross-section due to the combination of bending and shear. You need to verify whether the presence of shear force will reduce the bending resistance of the cross-section or not. It is highlighted that, when the coincident shear force VD less than 50% of shear capacity VPL, RD, no reduction in moment capacity is required. However, when the coincident shear force VD greater than 50% of shear capacity VPL, RD, thus the reduction in moment capacity is required. In our case, the design shear force is 0 at the midspan. Hence no check required. There are some examples of cases where you may need to check whether the coincident shear force will influence the reduction in moment capacity. Some more example cases shows here. Based on the lecture given, let's do some exercise. In this exercise, you are required to verify the resistance of the beam against the combination of bending and shear of the given cases. The solution will be given in our next class.